Have you ever driven past one of those massive industrial plants? You know, the ones with that incredible maze of pipes and tanks, and just wondered, how does all of that work? How does it all run in perfect harmony? Well, the secret is a kind of language, a universal blueprint that engineers use to build, well, pretty much our entire modern world. And today, we're going to decode it.
So let's start with this big question. How do you actually build a factory that runs itself? A place where literally thousands of parts have to work together, automatically, 24/7, without someone standing there pushing buttons all day. You have to start with a master plan, a diagram that shows not just what to build, but exactly how every single part talks to each other and is controlled.
And that master plan, it's called a piping and instrumentation diagram, or P&ID for short. Now, it's not a scale drawing, it's a schematic, but it is packed with an unbelievable amount of detail. It shows the functional relationship between every single pipe, sensor, pump, and controller. It is the absolute roadmap for the entire process.
I love this analogy. Think of a P&ID as the sheet music for an industrial plant. Seriously, each symbol is like a musical note, each line a measure, and when you put it all together, you get this incredible symphony of automation. So, in this explainer, we're going to learn how to read this amazing music.
Okay, first things first. It's really important to know the difference between a P&ID and its simpler cousin, the process flow diagram, or PFD. A PFD gives you the 30,000-foot view. It shows you what the process does. It's the simple melody. The P&ID, on the other hand, zooms way in to show you how it works. Every instrument, every valve, every single control loop. It's the full orchestration.
All right, so to read this blueprint, we have to start with the absolute basics. We've got to decode the symbols. You can think of this as learning the alphabet of the P&ID.
And here's the really cool part. This isn't some made-up language that's different at every company. It's standardized. It's universal. It's governed by industry standards like ANSI/ISA 5.1. That means an engineer in Houston and an operator in Hamburg can look at the very same diagram and know exactly what it means. It's a global language. And this language is built from just a few key types of symbols. You've got symbols for instruments, the things that measure temperature, pressure, you name it. Then you have symbols for valves that control flow, pumps that move liquids around, tanks to hold everything, and of course the lines that show how they all talk to each other. And this is just brilliant. It shows how much information is crammed into every single symbol. Just the way an instrument circle is drawn tells you exactly where to find it in the real world. A simple plain circle, that means the instrument is out in the field, on the equipment. See that circle inside a square? You'll find that on the main panel back in the control room. And a circle with a solid line through it, that tells you it's installed behind the panel, probably inside a locked cabinet. This is mission-critical info for operators and maintenance folks.
Okay, so we've got the pictures down. But in a plant that might have thousands of sensors, how do you tell one from another? Well, that's where the next layer of the language comes in, speaking in code. Every single instrument gets a unique name, or what we call a tag.
And there's a really simple, elegant logic to how these tags are built. Let's make one. First, you start with a letter for what's being measured. So in this case, T is for temperature. Easy enough. Next, you add a letter for the device's job, like C for controller. Put them together, and TC just logically becomes a temperature controller. See? It's a beautifully efficient system.
And this system covers all the big ones. F is for flow rate, L is for level, P is for pressure. Then you have the functions, like S for a switch, C for a controller, or I for an indicator, something that just shows you a reading. So if you see a tag that says LSH on a diagram, you can instantly decode it. Level switch high. It's telling you its exact job right in the name.
So we've got the symbols, and we've got the codes. But the real magic of a P&ID is watching how all these static parts work together. The diagram isn't just a list of parts, it tells a dynamic story. And the most important story it tells is about the control loop. This is what makes the blueprint come alive.
To really get this, let's look at a super common, practical example. How does a system automatically keep the liquid in a huge industrial tank at the perfect temperature without a person constantly turning a dial up and down?
The answer is the control loop, and it's basically a feedback system. It's a non-stop cycle of measuring a condition, comparing it to where it should be, and then acting to fix any difference. That's it. Measure, compare, act. Over and over again.
So, our little story here begins with a sensor. In this case, it's a temperature transmitter, which we now know would be tagged TT on the P&ID. Its only job is to constantly take the temperature of the liquid in that tank and send that information out as a signal.
That signal then goes to the brain of the whole operation, the temperature controller, or TC. The controller's entire purpose in life is to compare that live temperature reading to the temperature we want it to be, which we call the set point. It's constantly asking itself one question: is it too hot, too cold, or is it just right?
And if the answer is anything other than just right, the controller acts. It sends a signal out to what's called the final control element. In our story, it's a control valve on a steam pipe. If the tank is too cold, the controller tells that valve to open up a little more, letting in more steam. If it's too hot, it tells the valve to close a bit. This loop just runs and runs, non-stop, making tiny, precise adjustments all day long.
And of course, and this is so important, P&IDs are absolutely essential for safety. For instance, you might have a totally separate instrument, a high-level switch, or LSH, that isn't part of that normal temperature control loop. Its only job is to be a watchdog for an unsafe condition, like if the tank is about to overflow. And if that happens, it can trigger an alarm or even an emergency shutdown.
Now, it's obvious these diagrams are powerful design tools, but don't think for a second that they get filed away once construction is done. A P&ID has a lifelong job. It guides a facility from the very first sketch all the way to its final day of operation.
And this life cycle is key. During the design phase, P&IDs are used for critical safety reviews. During construction, they're the Bible for installing everything correctly. And once the plant is up and running, they are absolutely indispensable for training new operators and for safely managing any changes to the system. It is truly a living document.
So if there's one thing to take away, it's this. The P&ID becomes the #1 single source of truth for everyone involved. Engineers, operators, maintenance crews, they all refer to this one document to understand how the plant is supposed to work and to communicate clearly with each other. It makes sure everyone is on the same page, which, as you can imagine, is vital for both efficiency and safety.
And that really brings us full circle, doesn't it? It's so easy to look at these diagrams and just see a bunch of abstract lines and symbols. But the reality is, every single process product you use, from the gasoline in your car to the soda in your fridge, began its life on a diagram just like this one. It's a silent blueprint for an incredibly complex automated world. And now, the next time you see one of those plants, you'll know the secret language that makes it all possible.